Welcome back to the show, where we strip away the jargon and get down to the bare metal of how the world actually works. Today, we are doing something a little different. We aren't just discussing trends, we are testing our foundations.
That's right. It's easy to get lost in complex algorithms or massive grid architectures. But if you don't have a solid grasp of the first principles, the whole structure collapses. Today is about going back to basics, but with a critical eye.
Exactly. We've compiled a list of questions, some fundamental, some tricky, and some that separate the novices from the pros. I'm going to play the role of the inquisitor today. I'll throw these concepts at you, and I want you to break them down, not just textbook style, but with real engineering logic. Are you ready to be put on the spot?
I'm always ready. Let's see if we can spark some interesting discussions.
All right, let's flip the switch. We're starting with what sounds like the simplest question in the world, but it actually trips people up. In the purest engineering sense, what exactly is electricity?
It's a deceptive question because people think of power or energy, but strictly speaking, electricity is the organized movement of electric charge. Usually, we are talking about electrons flowing through a conductor because of a potential difference.
So, it's not magic, it's traffic.
Precisely. It's controlled electron traffic. You have a push that's your voltage, and you have the flow that's your current. If those electrons aren't moving in a directed way, you don't have electricity, you just have static potential.
Okay, let's scale that traffic up. We rely on the grid every second of our lives. But here is the classic debate. Why do we use alternating current, AC, for long-distance transmission instead of direct current, DC?
This goes back to the war of currents, but the engineering answer is purely about efficiency and mechanics. The primary reason is the transformer. With AC, we can easily step voltage up or down.
And why do we need to step it up?
To lower the current. See, transmission loss is calculated as I squared R current squared times resistance. If you double the current, you quadruple your losses. So, we step the voltage up to massive levels, which drops the current to a trickle, allowing us to send power hundreds of miles without losing it all as heat. Then, we step it down safely for your house.
That single concept, the transformer's ability to manipulate voltage, is basically why modern civilization exists.
It is. Without it, we'd need power plants every few miles.
Speaking of stopping that flow, let's talk about resistance. What is the unit? And physically, what is happening inside the wire?
The unit is the ohm. Physically, think of it as electrical friction. As electrons try to move through a material, they collide with atoms. These collisions slow them down and release energy, usually as heat. Resistance is simply a measure of how much a material fights against that flow.
Electrical friction is a great way to visualize it. Now, moving into the core concepts section. If resistance is the friction, there is one law that governs the whole road. Explain Ohm's law, but imagine you're explaining it to someone on their first day of engineering school.
It is the golden rule. Ohm's law states that voltage equals current times resistance. V equals I x R. It means that if you have a fixed resistance, the only way to get more current flowing is to push harder with more voltage.
It's linear.
Exactly. It's the relationship that defines everything. If you understand how those three variables dance together, you understand 80% of circuit analysis.
Let's apply that to safety. We use fuses in our homes and devices. A fuse wire usually has a low melting point, but high resistance. Why that specific combination?
It's a self-sacrifice mechanism. Because it has higher resistance, when current flows through it, it generates more heat than the surrounding wires, going back to that I squared R concept. If the current spikes to a dangerous level, that heat builds up instantly.
And because of the low melting point,
it snaps. It melts immediately, physically breaking the circuit path. It commits suicide to save the expensive equipment downstream. If it had a high melting point, it would just get red hot and start a fire instead of cutting the power.
A noble component. Now, here is a phenomenon that affects efficiency. What happens to the resistance of a conductor when the temperature goes up?
For standard conductors like copper or aluminum, resistance increases as temperature rises.
Why is that?
Heat is essentially atomic vibration. As the material gets hotter, the atoms inside are vibrating more violently. This makes it much harder for the electrons to navigate through. It's like trying to walk through a hallway where everyone is jumping around instead of standing still. You're going to bump into people more often.
That's a vivid image. And it's worth noting for our listeners, semiconductors do the opposite, right?
Correct. Semiconductors break the rule, but for standard wiring, heat is the enemy of efficiency.
Let's shift gears to heavy machinery, the industrial stuff. What is the fundamental principle behind an electric motor?
It's the relationship between electricity and magnetism. The principle is that if you place a current-carrying conductor inside a magnetic field, it experiences a physical force.
The Lorentz force.
Right. We take electrical energy, run it through coils to create magnetic push and pull, and that force is what spins the shaft. We are converting electron flow into mechanical rotation.
Now, here is a question that I know interviewers love to ask to weed out people who just memorize definitions. Why is a transformer rated in kVA kilovolt amperes and not in kW kilowatts?
This is the separator question. The reason is that a transformer doesn't know what kind of load you are connecting to it. It doesn't know if you're connecting a heater, which is purely resistive, or a giant motor, which is inductive.
And why does that matter for the rating?
Because the transformer has two types of losses: copper loss, which depends on current, and iron loss, which depends on voltage. Neither of those cares about the power factor of the load. The transformer heats up based on total current and total voltage, so we rate it in total power, kVA, rather than real power, which is kW.
So if you rated it in kW, you might overload it without knowing.
Exactly. You could have a low power factor, drawing massive current, and burn out the transformer even if the watts looked low.
Speaking of power factor, that's a term that scares a lot of facility managers. What is it? And why do industries get penalized for having a low one?
Power factor is essentially a measure of efficiency. It's the ratio of real power, the work actually being done, to apparent power, the total power being drawn from the grid.
So a low power factor means...
It means you are drawing a lot of current to do a small amount of work. It's like ordering a beer that is 50% foam. You're paying for the glass size, but you aren't getting much beer. Utilities hate this because they have to size their cables and transformers to carry all that foam, all that wasted current. So, they charge you a penalty to force you to install capacitors and fix it.
That beer foam analogy never gets old. It really visualizes the waste. Let's move to the think like an engineer round. These are more about design philosophy. If you look at high voltage transmission lines, the wires don't run straight forever. They swap positions. It's called transposition. Why?
It's about balance. If three wires run parallel for miles, the spacing between them causes unequal inductance and capacitance. One phase might have a higher voltage drop than the others. By twisting their positions at regular intervals, we average out those differences.
So it ensures the voltage at the receiving end is balanced across all three phases.
Correct. It also minimizes interference with nearby communication lines. It's a small design tweak that solves a massive headache.
Let's talk about the ground beneath our feet. Earthing. Why is it critical?
Many people think earthing is to protect the machine. It's not. It's to protect you. If a live wire touches the metal casing of a washing machine or a motor, that casing becomes live. Without earthing, if you touch it, you become the path to the ground.
Which is fatal.
Right. Earthing provides a path of least resistance much lower than the human body, so the fault current rushes to the ground, trips the breaker, and cuts the power before anyone gets hurt.
So earthing is basically the bodyguard of the electrical system.
Absolutely.
One last heavy concept before the rapid fire. On high voltage lines, sometimes you hear a buzzing noise or see a faint violet glow. That's corona loss. Why does that happen?
That happens when the voltage is so high, we're talking hundreds of kilovolts, that the electric field around the wire is strong enough to rip electrons off the air molecules. It literally ionizes the air.
The air itself becomes a conductor?
For a tiny distance, yes. That ionization creates a hissing sound, produces ozone, and results in a loss of power. It's why extra high voltage lines use those thick bundle conductors to spread out the electric field and reduce that stress on the air.
Fascinating. It's literally electricity trying to escape the wire. All right, we've arrived at the final stretch. Rapid fire round. I want short, punchy answers. Don't overthink it. Ready?
Let's go.
How do you control the speed of a DC motor?
Armature voltage control.
What is the unit of magnetic flux?
The Weber.
Why is silicon the king of semiconductors?
It's stable, cheap, and handles high temperatures well.
Is short-circuit current high or low?
Extremely high, dangerously high.
Why do we use circuit breakers instead of fuses in modern homes?
They are reusable. You don't have to replace them, just flip the switch back on.
And that is a wrap on the questions.
That was a good workout.
It really highlights that engineering isn't just about memorizing formulas, it's about understanding the why. If you know why the transformer heats up, you don't need to memorize the rating rule, you just know it.
That's the key. The formulas are just tools to describe the physical reality. If you can visualize the electrons, the heat, and the magnetic fields, the math becomes easy.
For our listeners, if you could answer more than 70% of these correctly, you're in good shape. You're thinking like an engineer.
And if you couldn't, that's fine too. It just means you have some specific areas to brush up on. Curiosity is the most important tool you have.
We want to hear from you. Which question caught you off guard? Was it the transformer rating? The fuse logic? Let us know.
And if you want us to go deeper, maybe into power system protection or digital logic next time, drop a request.
We'll be back soon to recharge your brain. Until then, keep questioning the world around you.
Stay curious and stay grounded. Goodbye, everyone.